In this video, you will learn about Bohr's theory of atomic structure and modern model of atom. Let's review where chemistry was after Mendeleev and Rutherford's contribution. Thanks to Mendeleev, chemists have a periodic table that summarizes the periodic chemical behavior of elements. And thanks to Rutherford, chemists knew basic of the atomic structure. But this Rutherford's model could not explain periodicity of the chemical behavior that was explained by Mendeleev. Therefore, an improved model that could explain the chemical periodicity was needed. The hint for such a model that can explain the periodicity came from examining light. This light is not the ordinary light, but it is the light that is given off when atoms of elements in their gas state were provided with large amount of energy. You are looking into these type of lights when you read a neon sign. Neon lights are glass-filled tubes with neon gas atoms that give off an orange-red light when supplied with electrical energy. Similarly, bright yellow light is given off by sodium vapor street lamps, and bluish pink light given off when hydrogen gas is electrified. Physicists passed this light through a prism. Passing a light through a prism was not new. Sunlight or white light passed through prism is separated or dispersed into its components. And the drops of water in air act like prism and gave us a chance to see the dispersion in the form of rainbow. Rainbow or dispersion created by white light is called a continuous spectrum because the colors in this spectrum smoothly blend into one another without any breaks. But a different type of dispersion is observed when physicists pass the light given off by a hydrogen or neon gas. They saw separate lines of colors, and this was a very astonishing discovery. Before that, no one have observed such a dispersion. This dispersion is called either a discontinuous spectra or line spectra, because the colored lines do not blend smoothly into one another. These line spectra were the hint for an improved model of an atom that could link the periodicity to the atomic structure. To understand this, first we have to look at the light and the characteristics of light. Light is two different things at once. It consists of particles or packets of energy called photons. At the same time, it acts as a wave of energy. For this topic, we will focus on the wave nature of energy. As a wave, light can be characterized by its wavelength. Wavelength is a distance between peak to peak or from trough to trough. So this distance between these two, peak to peak or trough to trough, is called wavelength and is the characteristic to identify the type of the light. Light of different wavelength is seen as different color. Light with a wavelength between 650 to 750 nanometer is seen as red color light. And the light with a wavelength between 380 nanometer to 430 nanometer is seen as violet light. And here in this slide, you can see the different colors of light have different wavelength. Indigo or violet light have a 400 nanometer, blue is 450 nanometer, green light is 500 nanometer, yellow is 590 nanometer, and red light is 700 nanometer. The wavelength between 300 nanometer to 750 nanometer is collectively called as visible light because these are the wavelengths our eyes are designed to detect. When all of these wavelengths impinge our eye at once, we see them as a white light. Outside the visible range of 380 to 750 nanometer, there are many other wavelengths, and these wavelengths are invisible to our eyes. All the invisible and visible wavelengths are collectively called as electromagnetic radiation, and the entire spectrum of this electromagnetic radiation is called electromagnetic spectrum. Even though we cannot see any radiation outside the visible range, it can affect us because all the electromagnetic radiation has energy, and the amount of energy depend on the wavelength of the radiation. In this image, you can see on the left hand side, I have a wavelength that is the largest, 10 to the 0, and as you go from right to left, the wavelength is decreasing, and gamma rays have the smallest wavelength. Wavelength and energy are inversely proportional, so for radio and television waves, where the wavelength is the largest, the energy is the smallest for that. And as you go from radio waves to the gamma rays, the wavelength is decreasing and the energy is increasing. Because of the higher energy, UV rays can cause sunburn, X rays can cause cancer, and gamma rays can kill us. So, what did we get out of this discussion is that each color of light has a particular amount of energy. And the fact that only four distinct lines are seen in the spectrum of hydrogen means that these atoms can only emit the four particular amount of energies or wavelengths, and not any other amount of energy. But why hydrogen atom gives off these certain energies? What is so special about these energies, and why does every atom of hydrogen behave the same way? The answer to this you will see in next few slides. In 1913, Danish physicist Niels Bohr proposed that electrons travels around the nucleus in circular orbits as the planets orbits the sun. You can see this in this image. We have nucleus, and outside the nucleus we have many orbits, and electrons orbits around the nucleus in these circular paths. He also introduced that the energies of electrons inside the atoms are quantized. Quantized means electrons could have only particular energy. This was the revolutionary part of this model, that electrons could possess only particular fixed energies, which in turn meant that only specific orbits at fixed certain distances from the nucleus are allowed. Before we go on, it is important to tell you that the scientific world quickly moved beyond Bohr's circular orbits. No one today believes that electrons orbit in atom's nucleus on fixed paths. The modern model of atom has very different view of how electrons behave in an atom. However, this does not mean that Bohr's model is not worth learning. Bohr's introduction of energy quantization and relationship between electrons' energy and its distance from the nucleus all are correct and are still part of the modern atomic model. In addition, Bohr's model is much easier to visualize than the modern model, and it works well in explaining periodic behavior of elements and why certain compounds have certain chemical formula. In Bohr's atomic model, electrons can jump from one energy level to another energy level, or from one orbit to another orbit, but they can never have energies between these allowed ones. Means these movements are quantum movements or quantum jumps. So electron can either be in this orbit, or it can be in the next orbit, but they cannot be in the middle of these two orbits. You can understand it by visualizing that electrons are positioned around the nucleus the same like a person standing on this ladder. A person on the ladder can stand on the first step, second step, third, fourth, and so on, but he cannot be found in between two steps. The same is true for the electrons in the Bohr's atomic model. Electrons can be on the first orbit, second orbit, or third orbit, but they cannot be found in the in between these two. Let's look at the electron shells, orbits, or energy levels. Bohr assigned a principal quantum number, which is represented by lowercase n, to each electron orbit or shell. Electrons occur in specific shells or orbits or energy levels. There are three names for this. Shell number starts from n equals 1 and they go up to the infinity. You can see in this image that we have a nucleus, and after that we have first shell, second shell, third shell, fourth shell, five, and so on. They will go up to the infinity. And the names that we use for these shells, we use electron shell, we can say orbits, we can say energy levels, and we also say principal quantum number. So these are all names for these shells around the nucleus. Let's look at the electron capacity in a shell. According to Bohr, each shell can hold a fixed maximum number of electrons, and that maximum number of electron in a shell can be calculated with the formula 2n squared. So if we calculate the maximum number of electron for the first shell, where n equals to the shell number, so n equals 1. So the first shell can hold maximum of 2 electrons. Second shell, based on this formula and calculation, can hold maximum of 8 electrons. Third shell can hold 18. Fourth can hold 32, and you can do this calculation for the rest of the shells. As the shell gets larger, they take electron farther away from the nucleus. The electrons, those are close to the nucleus, will have low energy, and the electrons that are far from the nucleus will have high energy. Ideally, all the electrons in an atom would like to occupy the shell of the lowest energy, which is n equals 1. So for instance, if we are filling the electrons for lithium with atomic number 3 that has 3 protons in the nucleus and 3 electrons outside the nucleus, so 2 of the electrons would go in the first shell and the third electron will go in the next shell. And this will be the electron filling for lithium. Let's see how to write Bohr's electron configuration. In Bohr's electron configuration, we start with the symbol of the element, and after that we write a right-hand parentheses symbol. The first right-hand parentheses indicate the first shell. If there are 2 right-hand parentheses, it means there are 2 shells. With 3 right-hand parentheses means that this element have 3 occupied shells. So for instance, for hydrogen, we have hydrogen and then the first shell, and there is only 1 electron in that shell, so we write down that electron like it is 1 electron. For lithium that have 3 electrons, we write the symbol of the lithium. This is the first shell, right-hand parentheses. Total electrons in the first shell is 2. That's the max the first shell can hold. And after that, there is only 1 electron left that will go after this second right-hand parentheses, which is the second shell. And we have this 1 electron in this outermost shell. For fluorine, we have the symbol of fluorine. First bracket is for the first shell. 2 electron is the max that can go in the first shell. The second bracket is for the second shell, and the second shell have 7 electrons. So total electrons in fluorine are 9, and 7 is the valence electron of fluorine. For sodium, we have 11 electrons. So the filling of 11 electrons is we have sodium. We have right-hand parentheses. This is the first shell. First shell have 2 electrons. Second parenthesis is the second shell. We have 8 electrons in the second shell, and this third parenthesis is the third shell, and we have 1 electron in the last or third shell. And you can see these the electrons in the outermost shell. These are the valence electrons. So hydrogen have 1 valence electron, lithium have 1 valence electron, fluorine have 7 valence electron, and sodium have 1 valence electron. Now let's use the understanding from Bohr's model to see why atoms exhibit chemical behavior of elements. Consider element lithium and sodium. Both are from group 1A, okay, and they have similar chemical properties. When we fill 3 electrons of lithium and 11 electrons of sodium, we get the electron configuration or electron filling as shown in this image. If you look closely, you will see the similarity between lithium and sodium electron filling. They both have completely filled inner shells. Lithium inner shell is first shell and it is completely filled with 2 electrons. Sodium have 2 inner shells, first and second. First shell can hold maximum of 2 and you have those 2 electrons. Second shell can hold maximum of 8 and you have 8 electrons here. So both lithium and sodium have completely filled inner shells. And there is only 1 electron in the outermost shell of both atoms. Lithium have 1 electron and sodium has 1 electron. The outermost occupied shell of an atom is called valence shell or valence orbit. According to Bohr, similar chemical properties of lithium and sodium are due to this similar valence shell electron configuration. Both lithium and sodium has 1 electron in the valence shell, and that is the reason they exhibit similar chemical properties in a chemical reaction. The other great success of Bohr's model was its ability to explain the line spectrum of hydrogen. Not only he was able to explain why line spectra exist, but he was able to calculate the energy values of the first 6 shells of hydrogen atom. In this energy level diagram, the absolute energies of shells are not so important, but it is the difference between them that is important. You can notice how energy differences between these orbits are getting smaller and smaller as the n or shell number increases. The energy difference between first and second shell is 10.2 electron volt. Between second and third is 1.9 electron volt. Between third and fourth is 0.7. Between fourth and fifth, it is 0.3. And between fifth and sixth shell, the difference of energy is just 0.1 electron volt. From this energy level diagram, you can find energies of electrons as well. For instance, if the electron is in the first shell, it will have the energy of 1 electron volt. If the electron is in second shell, will have the energy of 11.2 electron volt. Electron in the third shell will have the energy of 13.1 electron volt. And the difference in energies between these two shells is the energy that is required to move an electron from one shell to another shell. Another concept that you need to learn is energy states of atoms. There are 2 energy states, ground state and excited state. In ground state, electrons are arranged as close to the nucleus as possible. For a hydrogen atom which has only 1 electron, the ground state is shown in this diagram, and under normal condition, hydrogen atoms spend most of their time in the ground state. However, when enough energy is added to the atom, for instance by heating or by passing an electric current, its electrons can jump from the first shell or from the ground shell to the excited or higher energy shells. When this happens, we say that the energy is absorbed by atom, and now atom is in excited state. So in the excited state, one or more electrons are located in higher energy shells, even though there is room or there are empty shells available at the lower energy level. There are many possible excited states for hydrogen. For instance, a hydrogen electron can jump from n equals 1 to the second shell, third shell, fourth shell, and so on. So there are many possible excited states available for hydrogen. When a tube of hydrogen gas is electrified, the electricity supplied the energy to produce various excited states. And to understand the line spectrum exhibited by such a gas, we must understand what happened to the atoms after these excited states are created. As atoms do not usually remain in the excited state for a very long time, and also there are vacancies or space available at the lower level, so these electrons will eventually drop back down into these shells. And this process of dropping back to the lower energy levels is called relaxation. Um, to create an excited state, an atom absorbs a certain fixed amount or quantum energy. And for instance, when this electron from first shell is excited from first shell to the third shell, it absorbed 12.1 electron volt energy. And when it will relax back from the third shell to the first shell, it will release exact same amount, which is 12.1 electron volt energy. Similar to that, there are many possibilities for excited states. There are many possibilities for the relaxed states as well. So once we have the electron in the third shell, like in this example, it is possible that this electron can drop right back to the first shell after releasing 12.1 electron volt energy, or it can drop back to just the second shell after releasing 1.9 electron volt energy. Let's see relaxation and emission of light in hydrogen. When an excited hydrogen atom relaxes from the second shell to the ground state, the energy of electron goes from 11.2 to 1.0 electron volt, means that electron loses 10.2 electron volt of energy. This energy is released as light with a wavelength corresponding to an energy of 10.2 electron volt. I have this table here, and using this table, you can see that this particular electron transition, which is 10.2, is greater than 3.7. So this falls in the region of ultraviolet light. And because UV or ultraviolet light is outside the visible region, we cannot usually observe this particular line in the hydrogen spectrum. The observed line spectrum of hydrogen shows four lines in the visible region. We have one red, green, blue, and violet lines. And according to this table, the red line corresponds to the light with the energy in the range of 1.69 to 1.95. And from the energy level diagram of hydrogen, we can see that there is only one jump that corresponds to the energy in that range, and that jump is when electron relaxes from the third shell to the second shell and release the 1.9 electron volt energy that falls in this region. So you can see here in this diagram, when electron relaxes from the third shell to second shell, it releases 1.9 electron volt energy, and this 1.9 electron volt energy is seen as a red line in the hydrogen spectrum. Let's see how Bohr's model explains line spectra. Discrete lines in the spectrum of hydrogen are due to limited transitions and the quantum nature of the transitions. And emitted lines are a result of electrons relaxing back to the lower energy states and energy being released. One thing to remember is that Bohr's calculations failed to predict correct spectrum for any atom with more than one electron. And this model is replaced with current model of atom. However, his postulates that energy levels of electrons in atoms are quantized, and his rule for the maximum number of electrons that a shell can hold are still correct. And therefore, we will still use these aspects of Bohr's model while learning the correct or the current model of atom. Before we look at the refinement in the Bohr's model, let's write down Bohr's electron configuration for potassium. Potassium is from group 1A with 19 electrons, and group 1A atoms are supposed to have one valence electron. But when we write down the Bohr's electron configuration and you know how to write it, we have element symbol. The first right-hand parenthesis is the first shell, have 2 electron. Then second right-hand parenthesis have 8 electron. And then the third have 9 electron. Remember that the third shell can hold maximum of 18 electron based on the formula 2n square. So all remaining 9 electrons from potassium can go in this outermost shell. As you know, potassium is from group 1A, supposed to have one valence electron, but we are not getting that one valence electron for potassium using this Bohr's model. So this is another defect in the Bohr's model that we can resolve with the introduction of subshells within the shells. And that will be an important development of the modern model. The refinement in the Bohr's model was the introduction of subshells within the principal shells. This was more useful in predicting the chemical behavior of elements, and the subshells are given the single letter designations S, P, D, F, and so on, and that is the order of those letters as well. S subshell is the first shell within the level, P is the next, and so on. The number of subshells within a given shell is equal to the value of n, and the energy in the subshell increases in the order of S, P, D, and F, and so on, G and H. From this table, you can see if we have principal quantum number 1, or for the first shell, it will have only one subshell, and that one subshell will be S. Second shell can have 2 subshells, and those letters will be S and P. And third shell will have 3 subshells, S, P, and D. Fourth shell will have 4 subshells in it, S, P, D, F. Fifth shell will have 5 subshells, S, P, D, F, and G. You can pause this video to absorb the relationship between shells, number of subshells, and the letters associated with those subshells, and also look at this image to visualize how we introduce subshells within the shells. In this slide, I have a summary of maximum number of electrons of a shell and subshells. The maximum number of electrons in a shell can be determined with the help of formula 2n square. And based on this formula, the first shell can hold maximum of 2 electron, second can hold 8 electron, third can hold 18, fourth shell can hold 32, and fifth shell can hold 50 electrons. The number of subshell within a shell is equal to the shell number. For instance, the first shell will have 1 subshell, the second shell will have 2 subshells, the third shell will have 3 subshells, fourth shell will have 4 subshells, and fifth shell will have 5 subshells. In this subshell column, these numbers are the principal quantum number. So this S belongs to the first shell. This S belongs to the second shell. So it is 2S, and then we have 2p, 3s, 3p, and so on. The maximum number of electron that a shell can hold is fixed, and S can hold 2 electrons at max, P can hold 6 electrons, D can hold 10 electrons, F can hold 14 electrons, and G can hold 18 electrons, and so on. Also remember that subshells in a shell increases in energy in the order of S, P, D, and F. Okay, let's look at subshell crossing over. We learned from Bohr's energy level diagram that energy values of principal shells get closer and closer as the n increases. When we introduce subshells within these shells, the energies of some subshells can cross over with those in an adjacent shell. If you look at this energy level diagram with subshells, you will see that 4s subshell is actually lower in energy than 3D subshell. Additional crossing over you can see when we proceed beyond n equals 4. The consequences of these crossing is extremely important. Remember that Bohr stated that the ground state of an atom is achieved by filling the shells in the order of increasing energy. And this rule applies when we take subshells into account. So, and this actually solves the problem of electron filling of potassium and explains why potassium is in group 1A and shows properties similar to that of sodium and lithium. Let's see how subshells helps to solve the problem of electron filling of potassium and justify why potassium is in group 1A and shows properties similar to that of sodium and potassium. Remember that according to Bohr, elements with similar chemical properties have identical valence shell electron configuration, and potassium is from group 1A with lithium and sodium. And when we did the electron filling of lithium and sodium in the Bohr's shell diagram, we have one valence electron for lithium and one valence electron for sodium, but when we did it for potassium, we end up having 9 valence electron, and this 9 valence electron is not aligned with the Bohr's law that elements with similar properties have identical valence shell configuration. So let's fill in these 19 electrons in the modified Bohr's model that have subshells. So when we filled electron with, in this model, we have 2 electrons in the 1s, 2 electrons in 2s, 6 electrons in 2p, 2 electrons in 3s, 6 electrons in 3p, and 1 electron in 4s. The highest principal quantum number is 4 and have 1 valence electron. And this electron configuration is same as the configuration of lithium and sodium and is the reason why potassium exhibit same chemical behavior as lithium and sodium. Electrons are only in the first shell, so their first shell equals to their period number. For second period, you can see there are 2 occupied shells all the way from left to right, right? For the third period, there are only 3 occupied shells from left to right, and same is true for the rest of the periods. Fourth period will have 4 occupied shells. Fifth period will have 5 occupied shells. Sixth period will have 6 occupied shells, and so on.